In this paper, we propose to learn a condensed FEM model of a soft robot. We demonstrate that this compact model can be learned with a reasonable amount of data and, at the same time, be very efficient in terms of modeling, since we can deduce the direct and inverse kinematics of the robot. The finite element method is a powerful modeling tool for predicting the behavior of soft robots. Previous work show how finite element method-based simulation and inverse modeling can be used for controlling physical robots. However, its use for control can be difficult for non-specialists of numerical computation, as it requires an optimization of the computation to make it real-time. We propose to solve this problem using an approach based on data extracted from the simulation. Instead of directly learning the inverse model linking effector position to actuation effort as in previous works, we learn small-scale matrices that capture the mechanical behavior of the soft robot. The learned compact representation is not reserved to a single application, as these matrices could be used for different design and control applications. We now introduce the condensed model of a soft robot, with the example of a parallel soft robot named the diamond robot. With the finite element method, the robot is characterized by a matrix of 3D nodes positions. In the example of the diamonds, there is 4,884 degrees of freedom. We built our condensed model upon this FEM modeling through considering the covariance and free displacement matrices projected in the constraint space. Both these matrices only depend on the number of actuators and effectors, resulting in a space of small dimension. They capture the mechanical behavior of the robot in the input and output space, even the non-linearities. In the example of the diamond robot, the constraint corresponds to 4 actuators and 1 3D effector. We now present how we can deduce the inverse kinematics of a soft robot using the condensed FEM model. Both the distance between the effector and the target position, as well as the actuator's displacement, can be expressed as a linear combination between the condensed matrices and the actuation efforts. Using these two distances, we formulate an inverse optimization problem solved using mathematical programming. In the case of the diamond robot, we minimize the distance between the tip effector and a goal position in the 3D space, while considering physical limitation on the actuators. We now describe the computational workflow for computing the condensed FEM model. As a first step, data acquisition is performed in simulation. We sample in the actuation displacement space. Then, acquired data are used for training a multi-layer perceptron for prediction of condensed matrices. We use actuator length as the input of the network and quadratic reconstruction laws for the training. We now show an application of the learned condensed FEM model to the inverse control of the diamond robot. For the training set, the actuation space is decomposed into a grid of 9 points per actuator, which leads to 6,561 training samples. Using the inverse problem precedently introduced, we evaluate the inverse control of the diamond on a circular trajectory on its tip. The results obtained with both the FEM model and the learned model are comparable in terms of positioning. The second example we present is the finger robot example. The soft finger robot is actuated by 2 cables, and the objective is to control the position of its end effector. For training, we decompose the actuation space into a grid of 122 points per actuator, which leads to about 15,000 of training samples. After training the network, we obtain a reconstruction loss of about 10 power minus 6 for standardized data. With this learned model, we formulate an inverse optimization problem, where the objective is to minimize the distance between the goal and the end effector. The results obtained with the FEM model and the learned model are comparable in terms of positioning. In this example, we show that it's possible to control a complete robot by coupling learned model on some part of this robot. We use the learned condensed FEM of 1 finger to control multiple fingers. For a 2-finger problem, we create a new inverse problem where we introduce both the learned matrices for each finger and a coupling term that links the 2 fingers together. The problem is then to minimize the distance between the end effector and 1 finger and the goal, while keeping a constant distance between the end effectors of the 2 fingers. This mimics the presence of an object between the 2 fingers. The control of the goal enables to move both fingers simultaneously and to maintain their relative position, as we can see in the animation. In this work, we have shown the learning of a reduced mechanical model to control soft robots. This is a proof of concept under the quasi-static assumption. The dynamic case is left for future work. The learned mechanical model relies on much less parameters than the full FEM model, which enables to consider embedded control. However, it is sufficiently expressive to take into account the non-linearities of the underlying FEM model. We plan to consider two extensions of this work in the near future. The first one is the consideration of contacts. The complex is a good tool for characterizing the behavior of the robot in contact with its environment. This enables to consider object manipulation application. The second is design optimization. By varying the design parameters and giving them as input to the MLP, we want to create a direct and differentiable link between design parameters and learned mechanical quantities. This opens the path to the use of gradient-based algorithm for design optimization of soft robots. Thank you.